The photoelectric effect is a phenomenon that occurs when the surface of a metal is hit by electromagnetic radiation, such as light. That's the technical definition, but allow me to explain the photoelectric effect using an example of toll booths and traffic. When traveling on long roads, you are likely to encounter the occasional toll booth. These booths require you to pay a specific amount of money before allowing you to pass through. If you arrive at the booth without enough funds, your vehicle will not be permitted to continue. Alternatively, your vehicle will be granted passage if you pay the required toll amount. The photoelectric effect works in a similar way. When light, a type of electromagnetic radiation, falls on the surface of a metal, it ejects electrons from the surface. This happens because light is made of massless particles called photons, which possess a certain amount of energy. When these photons strike the surface, they knock electrons off. We call these photoelectrons. In our toll booth example, the approaching cars represent photons, their money represents the energy levels of photons, and the act of passing through the toll booth represents the photoelectric effect. You'd think that if a bright light, or in technical words, a high-intensity light, is directed at a metal surface, it would knock off quite a few electrons, right? Not always. Just because a light ray has a high intensity doesn't mean that it will cause the photoelectric effect. It can only happen if the frequency of the light rays is equal to or greater than a given value, known as the threshold frequency of the metal. Look at this graph. You can see that the number of photoelectrons emitted increases as the intensity of the incident light increases. When learning about the photoelectric effect, you'll often come across the term work function. This refers to the minimum amount of energy needed to remove an electron from a metal surface. If photons with enough energy hit the surface, they can transfer their energy to the electrons, allowing them to escape. If the energy of the incident photons is less than the work function, no electrons will be emitted, regardless of the intensity of the light. As you can imagine, work function and threshold frequency are closely related. Mathematically, the work function equals the product of Planck's constant and the threshold frequency. In simple words, if you know the value of a material's threshold frequency, you can determine its work function. In 1839, French physicist Edmond Becquerel first observed the photoelectric effect. Later, in 1905, renowned scientist Albert Einstein described the interaction between light and matter, revolutionizing our understanding of light. For his work, Einstein was awarded the Nobel Prize in Physics. The photoelectric effect has many practical uses in the real world, with the most significant being the generation of solar power. Solar power is one of the most reliable forms of renewable energy, working by converting sunlight into electricity through photovoltaic technology, or PV. In photovoltaic cells, or PV cells, when sunlight hits semiconductor material, such as silicon, it creates a pair of electron holes. Electric current is produced when these electron hole pairs are separated by an electric field. PV cells have many applications, including cars, homes, traffic lights, buildings, satellites, and space stations. For instance, the International Space Station, the most expensive structure ever built by humans, is powered by an assortment of solar panels made of PV cells. The photoelectric effect is used in solar power in various devices, such as photodetectors in cameras, burglar alarms, and industrial automation. It is also used in light meters for photography, films, theater lighting, X-ray imaging for medical diagnosis, spectroscopy, electron microscopes, atomic clocks, automatic doors, elevators, and barcode scanners. These diverse applications all stem from the photoelectric effect. The photoelectric effect is like the cool folks only club of the quantum world. If your light's not bringing the right energy to the party, the electrons won't be impressed.